China may have just built something that could make copper obsolete inside the most powerful AI chips on the planet. It's not a processor, it's not memory, it's glass. And if this actually scales, it could change how AI computers get built for the next decade. China may have just taken a major step toward moving one of the most critical parts of AI hardware away from organic circuit boards and into glass. BOE, the Chinese company best known for its display panels, announced it completed a high-layer count glass core substrate sample for advanced chip packaging. The piece follows a 9-2-9 architecture with 20 layers total. What matters most isn't just that the sample exists, but that it passed some tough reliability testing. 1,000 thermal compression bonding cycles, moisture testing, high and low temperature storage, and preconditioning. This doesn't mean China is mass-producing a finished AI processor built on glass. It doesn't mean silicon is out the door, and it doesn't mean copper is vanishing overnight. What it does show is that glass packaging is moving past lab demos and into hardware that can actually survive real manufacturing and operating stress. On top of that, BOE is putting together a dedicated team to develop micro-LED optical interconnects and co-packaged optics built on glass substrates. The underlying idea is that the next big bottleneck in AI systems might not be raw compute power. It might be the copper wiring itself, carrying data between processors, memory, and networking components. If glass allows for bigger packages, finer wiring, better dimensional stability, and optical links placed closer to the chip, it could completely change how future AI computers get assembled. Did China just build a 20-layer glass AI chip that could kill copper? Not yet, but it cleared one of the tests needed for that possibility to start being taken seriously. So what did BOE actually build? A modern AI accelerator isn't just a single slab of silicon. The finished product can include multiple compute chiplets, high-bandwidth memory stacks, power delivery components, controllers, and communication links. All of that has to be positioned, powered, cooled, and connected with enormous precision. The structure holding it all together is called a package substrate. It sits between the silicon dies and the system board, carrying power and signals across thousands of tiny electrical connections. Right now, most advanced substrates are organic, but as packages get bigger and wiring gets denser, organic materials start hitting physical limits. They can expand, shrink, bend, or warp with temperature changes. And when you're aligning extremely fine connections across multiple chiplets, even a tiny dimensional shift matters. Glass offers a different foundation. It stays flatter across large areas, gives better dimensional stability, supports very fine features, and has favorable electrical properties for high-speed signals. BOE's 20-layer sample uses a 9-2-9 configuration, 9 build-up layers on one side, a 2-layer glass core in the middle, and another 9 layers on the opposite side. This design matters because advanced packages need lots of routing layers to distribute power and connect processors, memory, and external interfaces. Building a substrate this large that stays aligned and reliable is genuinely hard. That's exactly why the reliability testing matters. Computing hardware constantly heats up during operation and cools down when it's idle. Different materials expand at different rates, and that creates stress around copper vias, solder joints, wiring layers, and interfaces. High temperatures weaken materials, while low temperatures can cause contraction and cracking. Manufacturing steps like thermal bonding add even more heat and pressure before the package ever reaches a customer. BOE says its samples passed several industry reliability tests, including 1,000 thermal compression bonding cycles, accelerated temperature and humidity testing, biased humidity testing, high and low temperature storage, and preconditioning. None of this guarantees the substrate will hold up in every product, every factory process, or every real-world environment. What it shows is that a complex multi-layer structure can keep working after repeated environmental and manufacturing stress, which is exactly what chip companies need before trusting a new substrate under extremely expensive processors and memory. The reason this matters is that AI packages continue getting bigger every generation. A single package can hold several compute dies along with multiple stacks of high-bandwidth memory. One piece of silicon can't grow forever. Manufacturing defects become more expensive as die size increases, and practical size is limited by lithography equipment. Instead of building one giant chip, companies split large designs into multiple chiplets and connect them together inside a single package. That approach solves one problem, but creates another. The substrate now has to connect many different devices with enough bandwidth that they behave like one processor. It also has to remain flat enough for thousands of microscopic connections to line up perfectly while supporting much larger physical dimensions without warping. That's why glass has become so attractive. Glass can potentially support larger package formats than organic materials while maintaining much tighter dimensional control. That doesn't automatically make it cheaper or easier to manufacture. Drilling extremely small through-glass vias is difficult. Filling those holes with copper is difficult. Cutting large glass panels without introducing cracks is also a major engineering challenge. BOE says it has developed several key manufacturing capabilities, including high aspect ratio through-glass via formation, deep-hole copper filling, low-stress metallization, multi-layer lamination, high-density routing, and low-stress cutting. Those processes transform an ordinary sheet of glass into a functional electronic platform capable of carrying both power and data. But what about copper? Despite the headlines, copper isn't disappearing from electronics. Even BOE's own glass substrate still depends on copper-filled vias and metal routing throughout the package. Power delivery will continue requiring conductive materials, and short electrical connections aren't going anywhere anytime soon. The real challenge isn't copper itself. The problem is distance. As data rates continue increasing, copper links consume more energy and become increasingly difficult to operate reliably over longer distances. Electrical signals lose strength, generate more heat, interfere with nearby channels, and require increasingly complex signal correction techniques. Inside modern AI servers, processors and memory exchange enormous amounts of information every second. Engineers continue improving copper interconnects, but the energy required to move each bit of data is becoming one of the biggest limitations on future AI performance. That's where optical communication enters the picture. Instead of transmitting information as electrical signals, optical links use light. Light can carry much more data over longer distances with lower signal loss and significantly less electromagnetic interference. The industry already relies heavily on optical transceivers inside data centers. The next logical step is moving those optical components much closer to the processor itself. This concept is known as co-packaged optics. Instead of sending high-speed electrical signals from a processor across an entire circuit board to a separate optical module, the optical engines are placed directly beside, or even inside, the processor package itself. That dramatically shortens the electrical path, reducing power consumption while allowing much higher bandwidth. This is where glass becomes especially valuable. Glass is dimensionally stable, supports highly precise structures, and provides an excellent platform for combining both electrical routing and optical components inside the same package. BOE says it has formed a dedicated project team focused specifically on micro-LED optical interconnect systems and glass substrate co-packaged optics. Micro-LEDs are best known from display technology, but they're also extremely fast light sources that could become ideal for short-distance optical communication. A micro-LED array could transmit many optical channels simultaneously, allowing future AI servers to move enormous amounts of data between nearby processors and memory, while consuming much less power. BOE also brings something unique to this field. The company has decades of experience manufacturing large glass panels for displays. Although display production and semiconductor packaging have very different technical requirements, many of the underlying manufacturing techniques overlap. BOE already has expertise in large area glass processing, precision patterning, multi-layer structures, and highly automated mass production. Those capabilities can potentially be adapted to advanced semiconductor packaging. In fact, BOE already operates a pilot production line for glass core substrates with a reported design capacity of roughly 1,000 substrates per month. The company also says it has delivered samples to domestic customers, with some reportedly completing concept verification and moving into technical testing. However, it's important to understand what that actually means. A pilot production line is not the same as mass production. BOE itself acknowledges that this business has not yet reached commercial-scale manufacturing and has not generated mass production revenue. Producing a few successful samples is very different from manufacturing thousands of identical substrates with high yields, low costs, and consistent quality. Every substrate used inside a commercial AI processor must meet incredibly strict specifications. A tiny defect could ruin a package containing processors and memory worth thousands of dollars. The real challenge isn't making one good sample. It's making thousands of them reliably and economically. China also isn't alone in this race. Intel has spent years researching glass core packaging, while substrate manufacturers, foundries, equipment companies, and display makers around the world are all developing their own glass technologies. The reason is simple. Every major AI chip company wants larger packages, higher memory bandwidth, more chiplets, lower power consumption, and faster interconnects. Glass may become part of that solution, but it almost certainly won't replace everything else. Organic substrates continue improving. Silicon interposers remain essential for extremely dense connections. Fan-out packaging, advanced bridges, and new redistribution technologies are all evolving alongside glass. The future will most likely combine multiple packaging technologies rather than relying on a single material. What makes BOE particularly interesting is its manufacturing scale. If the company successfully adapts large panel display manufacturing to semiconductor requirements, it could eventually produce advanced substrates using panel-level processing instead of treating every package like an individual wafer. If that happens economically, BOE could become one of the key suppliers underneath the next generation of AI hardware, even without manufacturing the processors themselves. The next milestone won't be another laboratory record. It'll be customer qualification, production yield, manufacturing cost, and real deployment inside commercial AI systems. Because the race for AI leadership is no longer happening only inside the transistor. It's happening underneath the chip, between the memory, and across every connection carrying the data. So what do you think? Will glass substrates and optical interconnects become the foundation of the next generation of AI hardware? Or will today's packaging technologies remain dominant for years to come? Let me know your thoughts in the comments. And if you enjoyed this breakdown and want more deep dives into the future of semiconductors, AI, and cutting-edge technology, make sure to subscribe to Chip Wars and turn on notifications so you never miss a video. Thanks for watching, and I'll see you in the next one.